In our study of physics, many times we're confronted with quantities that are simple, they're scalar. Scalar meaning that they just have a number associated with a unit. So if I have an object, it's going to have a mass, and if I said its mass was 2 kilograms, that's a scalar quantity. But a lot of times we're going to find quantities that have both magnitude and direction, and here's an example of one on this slide for a displacement. You can imagine that somebody decided to walk 2 miles east, and then they walked 1 mile north. So they were following a path here, and they ended up at a location right here. If I draw a vector or an arrow from the origin to this final stopping point, that's going to be a vector. Notice that it's going to have a length, and it also has a direction or an angle that it makes with this east axis. And so this is a nice simple example of a vector. Note also that you had some displacement to the east, or you walked some distance to the east, and then you walked some distance to the north, and this ended up forming a nice little right triangle, which allows us to say something first about the length or the magnitude of that vector. So drawing it out again, pointing out that this is a right angle between the east component and the north component, or these two sides, we see that Pythagoras' theorem is going to give us the length of that vector, or the length of that hypotenuse. And so here we just write d, the length of this green vector here is going to be the square root of 2 miles squared plus 1 mile squared, and we end up with 2.24 miles. We're going to have vectors in a lot of problems where we're going to be adding vectors together. Let's say you walked, 2 miles east, and then you had some other path that you walked, another displacement b, where you made some angle with the east axis, and you end up in some final location shown here. Well, you can add both those vectors together graphically by drawing a first, and then at the head of a, put the tail of b and draw it out, and then connect the tail of a with the head of b, and you get that final vector. You want to look in your book at the examples for this operation to make sure that you understand how to do it graphically. It's pretty straightforward. Now, most of the time when we're working problems, we're not going to be adding vectors graphically. We're going to break them down into components and add those. In order to do that, we have to notice a few facts about right triangles. Now, trigonometry, the science of triangles, is going to give us relations between the lengths of the sides of triangles and the angles in a triangle. And this is going to allow us to do important manipulations of vectors. In this diagram, what we see is that if I have a right triangle where the length of the adjacent side is a sub x and the length of the opposite side is a sub y, that's adjacent and opposite in relation to this angle theta. The ratios of the sides of the triangle are going to be related to the trigonometric functions of theta. Or maybe better to say is that the trigonometric function is going to give you the ratios of the sides of the triangle. So we define first cosine of theta. Given this right triangle, the cosine function, which you'll see on your calculator, if you operate cosine on theta, it's going to give you the ratio of a sub x to that hypotenuse, as shown here. In the same way, sine of that angle, the sine function is going to give you the ratio of a sub y over a here. And then finally, the tangent function gives you the ratio of a sub y to a sub x. If you've already had trigonometry, then you're familiar with these, and it's certainly good to refresh them. If you're not familiar with these, then you'll want to make sure you go into the book, read the explanations of these trig functions, and work through those examples, never, of course, hesitating to email me or set up a Zoom session so we can discuss these. The value of these trig functions and these relations is it allows us to go from one representation of a vector to another, meaning that if somebody told you what a and theta were, you can use these trig functions to calculate a sub x and a sub y. And the opposite holds true as well. If somebody gave you a sub x and a sub y, you would know everything about that vector, and you could use those to first calculate the length of the hypotenuse using the Pythagorean theorem, and then you could use these relations, these trig relations, to calculate the angle theta. the reason we looked at these, the reason these are useful, I'm arguing in this case, are that these allow us to do vector addition using components. So as we go into the process of adding vectors by components, you're going to want to look at each vector. And remember that I had a relationship for cosine of theta, where cosine theta was equal to a sub x over a. When you're adding up these vectors, you're going to want to find the x component of a and the y component of a. And this is going to be the relationship that allows you to do that. You've just done an algebraic manipulation on your definition of cosine to write a sub x equals a cosine theta. And right now, especially if you're not familiar with trigonometry, that's going to sound like an odd expression, but you're going to use it so much that a sub x equals a cosine theta and a sub y equals a sine theta are going to be second nature to you quicker than you think. So when you're adding vectors together, you're going to perform these operations, taking the hypotenuse or the magnitude of that vector times cosine of the angle that it makes with the x-axis to find the x component. Similar thing with the y component. And you're going to be adding these x and y components. What this diagram is doing is arguing that the vector a shown here is actually the sum of an a sub x vector and then an a sub y vector shown there. And then when you want to find the magnitude and direction of it, you first use the Pythagorean theorem to get the hypotenuse, given that you knew a sub x and a sub y. And finally, they've just written out tangent theta here. If you know a sub x and a sub y, you can take the ratio of a sub y to a sub x and then take the inverse tangent function in order to find theta. Again, I can't stress this enough. You need to go through the examples in the book to make sure that you understand your trigonometry, even if you've had it before. And if you haven't had it, you need to go through those examples to learn these simple operations that you're going to use over and over. And as always, never hesitate to contact me if you want to work through these or get more examples.